Today I'm going to talk about variational quantum supervector machine, which is the quantum machine learning model that I've been working for. And it got finally published, so I'm doing this presentation. So like I said, this is my project, so I was going to give very long and detailed talk, but today I'm not feeling so great, so I'll make it brief as possible. Okay, so what's a supervector machine? Yeah, it's one of the basic machine learning algorithm to classify two data into two classes using the plane, hyperplane, represented by red line. But yeah, as in the left figure, it'd be great if we can classify every data in a straight line like that, but unfortunately that's not the case. So what we do is so usually the data is distributed and we want to classify. So what we do is we map the data using feature map 5 to another higher dimensional space, which we expect them to be linearly classified. So the data or vector that consists this two supervector plane is called supervector, and as I will discuss later, the weight given to this supervector with the non-zero and everything else, weight for everything else became 0. So this is the mathematical formula. So this W is the vector that represents the hyperplane. So, and this term is related to penalty. Penalty term that. Yeah, this term is penalty term, like a cost term. So ultimately, all the data should be in either this side or this side, but some of the data can penetrate through this plane. So the amount that penetrate will be represented by slack variable eta. Theta. What was it called? Yeah. Well, we want to minimize that kind of penetration. So this is the optimization function that we want to tackle. And to make it easier, we can use strong duality and transform this equation to this equation. So P star and D star are the same. And well, in here we have 3 kinds of variables. Vector, the terms related to hyperplane and slack variable, and if we transform it, we can represent all this in a single term beta, which is kind of a weight given to each data. So this is the equation, and we can optimize it and solve what's the optimal beta and fit that into this equation, which we can do a classification of the data. 민수 잘 들려? 소리가 없네.
예, 잘 들립니다.
Okay, so since this is almost one of the basics and very representative model, many algorithm has been developed to make this classical supervector machine algorithm to quantum one. So one of them is least square quantum supervector machine in 2014. The important thing about this algorithm is that it is the one of
it is one of the algorithms that shows quantum advantage or exponential speedup compared to a classical counterpart. And however, it requires subroutines like QRAM and HHL, matrix exponential, which is not feasible in these computers. So it's good, but not practical. And the other algorithm is called variational quantum circuit and quantum corner estimator. I guess I have to explain details on this one. So it was proposed by researchers in IBM in 2019. So I'll skip part about variational quantum circuit, but I'll explain more on quantum corner estimator. So here the K is called corner. It represents the relation between two points of data. Can someone open the door? It's kind of getting really hot. Open the door? Yeah. 아니면 저기 온도를 낮춰야 되나? No. 그냥 그럴까? So basically, what we do here is, so basically, quantum corner estimator do here is estimate this corner using quantum circuits. So like this one, and make this corner matrix. So they're estimating each corner element separately. So that means we have to measure about m square terms, where m is the number of data you're using. And for bounded quantum, so basically what they're doing is construct a quantum circuit and measure, right? We want to get some expectation value of some operator, right? That requires number of measurements, like something like this, for error. But since we need to repeat this about m squared times, the error propagates, right? So in terms to get corner matrix, let's say this is estimated and this is 0. To get a corner matrix that has error less than this one, we need to measure about so the number of measurement is quite big. So it's 4 내 제곱을 영어로 뭐랄까? 건제곱. So it's powerful. And if you think about it, corner, like if you're constructing corner matrix classically, you need to, there's this amount of elements, so this should be the complexity of calculating corner classical. So compared to this, this is very inefficient, right? So why they're using this? They claim because they're using shallow quantum circuit that is not tractable, which means it cannot be simulated easily on classical computers. So we can represent more feature maps, which is in a protocol. So since we can represent more feature map, we can separate data more easily. So we can map the data to higher dimension. So that's what they claim about their algorithm. So the advantage can be given from that. Okay, so what I'm basically doing is to use this kind of quantum corner algorithms, but to improve the complexity in terms of time. So like I said, basic superfect machine optimization equation would be like this. And I did some little mathematical tricks to reduce like this. And the classification would be change. Oh, you cannot see my mouse, right?
Oh, we can see.
Oh, okay. Yeah, so I managed to change this equation to this. And I defined these three terms to represent the optimization equation and the classification equation. So these upper two terms would be the some kind of cost term and some kind of regularization. Okay. The reason I did this is it turns out these three terms can be estimated efficiently on a quantum circuit. Okay, so this term would be the classification or decision function. Okay, so these are the circuits. Each component. So U maps or encodes the classical data to some kind of quantum states, and V is just some answers that we expect to encode the alpha, which is the weight I mentioned before. So using this kind of quantum architecture, after this say preparation stage, we have the quantum state like this. So this quantum state would be the state of this level. Okay. So we use swap test to get these two functions. Any questions so far? Try not to mathematically follows because it's really easy math, but you have to do it on paper, so try not to follow. Okay, so the features about this circuit is that the depth of this circuit will be linear in the number of data. So as I mentioned, this one, so we are trying to get some expectation value, right? So, and the depth, which is proportional to the time we need to spend to execute this circuit. So combining with this one, we get runtime like this for each measure. And this is a regularizing circuit, which is prepare these two ansatz and the CNOT gates sequentially and measure and the success probability of measuring all 0 bit is same as regularization. Okay, so this is the total procedure or scheme of my algorithm. So it is variational algorithm. It is something like VQE. Okay, so we input some parameters to our circuit, and circuit returns objective function value, which we use it to do a sequential, not sequential, repetitive optimization. And we get the optimal value theta, which is a parameter for this quantum circuit. We feed into another circuit and get the decision function and classify the equation, classify the new data, unseen data. So I want to. Did I skip? Okay. I want to add some remarks on this part. Sorry, on this part. So the number of parameters that would be something like polylog of and is like a log m something like 2, 3, 4, 7. Okay. This is because the type of encoding I use for this V answer. So number of qubits required for this answer is log m, right? Because I'm using amplitude encoding here, not exactly amplitude encoding and something. So for this V, since we have no prior information, it's typical to use hardware efficient ansatz, which is something like there is circuit and there's entangler, and we repeat this layer many times, right? So that's why the number of parameters is proportional to number of qubits, which is so that's why the number of parameters we required is something like polynomial. Okay, so since we are using something like gradient descent, the runtime complexity we require is something like time for running circuit, each circuit times the number of parameters. So that's why the total runtime complexity will be m polylog. Can see. Okay, so why this is good is that compare the class runtime complexity of classical algorithm is actually something like square, or if you think naively is cube, but using a most advanced algorithm is other m times m squared. So compared to this, it has lower time complexity. Not to mention this one. Okay, so why this happened? Because I'm trying to measure optimized function itself. I mean, objective function itself instead of each column element. So we're not doing like this, but instead we measure the objective function. So that's why we only need to measure one value instead of m square values. So that's why it exerts more. It can show lower complexity. So this is a summary, but we can skip it. So I run this on a IBM Q machines as a proof of concept, which I think I can skip it. Okay. And for numerical demonstration, I use Iris data set. I think I can skip it. So, but bottom line is that have you guys know something called Barron plateau? Yeah, so I was worried since this is hardware efficient ansatz, it is very vulnerable to Barron plateaus. And what we see here is that it is true. It is very vulnerable to Barron plateaus. However, since this is a classification algorithm, the exact value of the decision function itself doesn't matter. Only the sign matters. So if you compare on accuracy, we still have barren plateaus, but compare in terms of accuracy, it's okay. So that's the kind of a main result of this numerical demonstration. Okay, so what we need to do further is not to use naive hardware restriction ansatz, but some other ansatz that has some symmetry or avoids barren plateau. Okay, so what I'm trying to look for is well, like I showed you, what this should do is to encode weight alpha, right? But from the strong duality, alpha should be very sparse. Which means most of the alpha I is zero, right? Which corresponds to training data, which is not support vector. But some alpha that is support vector is non-zero. So I'm trying to look for ansatz that encodes this kind of condition, or you can call this symmetry. Yeah, so if you guys have some insight, I'll be glad to hear about it. So that's the main feature studies from this work. So this work has been published to a scientific report. I can give you a paper if you want. Okay, thank you very much. Any questions?
So for the last part that you just mentioned, isn't that something that we can do with like something like Grover's algorithm, like increasing the amplitude of some specific item that we want to like look for?
What would be the oracle?
I have no idea.
Yes. So yeah, I tried that idea or something like that. So instead of oracle, which we don't know, I just put random ansatz as an oracle and hope that it works, but it didn't.
Like when you see that in the barren plate problem, the accuracy is good, but there's a barren plate. What do you mean by that?
Oh, so yeah, I'll okay, the value delta here means the difference between the theoretical minimum of the objective value and the minimized objective value from gradient descent. So delta increases as the number of qubits, or yeah, the number of qubits increases. To be more exact, I need to analyze the gradient or gradient variance, right? But I did that too, but I don't have a figure right now. So what this means is that as number of qubits increases, it is harder to get a minimum because of the vanishing gradient. So that's why it has I said it's very vulnerable to barren plateau, like any other variational algorithm using hardware restriction.
But how does your like ansatz sketch when you increase the number of qubits? Like, is it like, for example, what if the problem is with the ansatz, it's not expressive.
It is general ansatz that you're that you know. Okay, so like
Very efficient.
yes. So yeah, it is the expressibility limits, right? If you increase the number of layers, the expressibility limits. But still, it is very vulnerable to baryon collapse, right?
Okay.
Yeah.
Yeah, but like, what if it could be, since you increase the number of the qubits, you also like do some modification in the data, right? Like the data you used.
What do you mean
So,
modification?
like, what is the number of qubits in these
Oh, the number of qubits for these answers.
for the answer and
Yes.
for like in terms of the problem?
In terms of problem, so if you M is the number of training data we try to learn.
Process, right?
Yeah, and this log M is the number of qubits for the answers. So yeah, that's the relation. So if we input more training data, which we should, it becomes it needs to have more qubits and it's harder to train.
I think one more question is that like QC, you say
Yes, yes.
maybe previous, like you were reviewing the paper, I guess.
Yes, yeah,
this one.
this one.
You say it's not better than the classical method.
Yes.
But so like the complexity is not better than the classical.
Mm.
Right? But how is the advantage of this?
Because you can really track this. It's a conjecture. They actually mentioned in the paper that it is a conjecture. But since this is a circuit for measuring each codon element, you cannot simulate it classically, so it can represent more Connor functions that is not expressible in analytical or classical. Right?
But they don't have practical results, right? Like, is it possible to say it's practical? Like theoretically, yeah, since it's not simulatable, you can say.
Well, it does map data to exponentially larger Hilbert space
Okay, yeah.
easily. Right? So I guess it kind of makes sense, but if you also think about Gaussian kernels, that is also mapping data to infinitely high dimensional space. So, yeah, it depends on your problem, I guess.
Now, can you show the circuit, the training circuit part, or the whole part? Yes, yes. I'm just a little confused that, so the N is the number of data there, right?
Yes.
Which corresponds, which like right next to I and J.
Hmm.
And well, what is N?
Where's N?
Like below M.
Oh, here. Oh, here. Okay.
Yeah,
So small m is just log m. I didn't want to
Log N.
yeah
okay.
write a long and n is just the number of tweets we need for the data. So and you can think of it as n as a dimension of each data.
Like feature.
Yeah.
So you're basically calculating the fidelity of 2 data points every time, and then you just repeat it. Is that what you're doing, or
2 data points at the same time.
at the same time?
Yeah. So to get the object function.
Right,
So,
right.
yeah.
So that means you need to run that circuit like n squared time. Is that what you're
No.
saying?
No, that's the problem of this quantum corner estimator.
Okay.
So yeah, each circuit measure an element. So it,
Right, yeah.
but this one, it returns the objective function that you want to minimize. So you need to measure only one value. But since you're doing the optimization, think of it as this way. If you want to calculate the gradient, estimate the gradient, well, you're going from one scalar to vector, which is length of the number of parameters. Right? So that's why you need to repeat it proportionally to the number of parameters.
Is there any exact circuit plot for the U gate next to B theta?
Yes. So I come up with this game. So here, this one, we assume we know. We know the each gate component of this gate. Okay.
Upper one.
Yeah, upper one, to make this upper one is the problem. So since we know all this gate component of this this gate, we transfer it into single rotation gates and two cubic gates, right? And condition all the single cubic gates using methods shown in this. So what this do is condition on all states. So so if this is 0, 0, 0, it gives certain value, and if this 0, 0, 1, it gives a different value. Okay, so that's what this one did. So, and it said this scales as square. I'm sorry, exponentially on the number of qubits, which is logarithmic on the number of data. So all these scales as linear to the number of data. So I did some numerical simulation on this circuit depth scaling. Yeah, and it shows like this. So it is indeed scales linear, but you can think of other methods to implement this color U. Okay.
X0, Y0, I is the initial state is prepared with superposition of data.
Actually, for I or J registers, it is a smart thing to prepare in the superposition of all state, which is just other method. Yeah. But for this one, other ones, you don't need to, and especially for this ancilla, it should be reset to 0.
So the data initial state was prepared at QM X2.
What do you mean next step?
What is the input for X0?
Oh, this is just indexing numbering. So you can just reset in any state, any specific state, and the actual encoding of the data happens here. So you can think of these as a initial state preparation. And this is the operation and this is measured. Like that. Okay.
I found that if I remove y0 and y1 of the circuit, I could express the quadratic term. So can I use it for quadratic optimization, or are there any constraints like convex or positive semi like that?
No. Yes, you can remove these registers and set up a quadratic equation, except the condition is that alpha should be larger or equal to, and the norm should be 1. Except that, yeah, you can do it. Okay, if you don't have any more questions, it's longer than I expected. So thank you for listening.